Okay, thanks everyone for coming here. I will talk about our work on QCA and Floquet code. So this is our account number. If you're interested, please check it out. Okay, so the motivation of our talk of this talk is a puzzle in the Floquet code. This is a cartoon for the Floquet code proposed by Christian and Ha. So what they do is that they consider some coloring in the 2D lattice, where they colored or they placate by RGB, and then they all the color all the edges by RGB, so that like say an edge between a red color and a yellow color, a red color and the green color will be the blue color, etc. And then they have a period 3 measurement where they measure XX on all the red edges, and then they measure YY on all the green edges, and then they measure ZZ on the blue edges. So what happened in this protocol is that after each measurement, after each time slide, the system will be in torical state. So on torus, there will be 2 logical qubits. And what's more interesting is that it shows that by looking at the measurement outcome of the whole history, they can do some kind of error correction. And of course, in reality, we do not want to implement this protocol on the torus. Instead, for example, in the static Tori code case, what we do is that we want to introduce some kind of gap boundary condition, and we implement this thing on disk. So it's quite natural to try to introduce some kind of like nice gap boundary of this Floquet code. However, people have tried a lot, but it seems that it looks impossible. So the purpose of this talk is to rigorously show that this kind of no-go thing is something intrinsic and fundamental. Okay, so to solve this puzzle, let me remind you a story about the local unitary circuit. Here by local, I mean local in the sense of physics. So it has some kind of spatial structure. Let's say in 1D, we can consider some kind of brick wall construction like this. So this one will be the spatial direction, and this one will be the time direction. And on 2D, you can also consider a similar brick wall construction. And here I only show 2 layers of the unitary, and the time direction is perpendicular to the page. So yeah, like this. So a paradigm that appears frequently in physics is to consider the lower dimensional boundary of the high dimensional bulk. In this case, let's consider the 1D boundary of the 2D bulk. What's interesting is that even if the 2D unitary circuit is trivial in the bulk, it can still introduce something non-trivial on the boundary. And to be more precise, in this case, the 1D boundary is what we call a 1D quantum cellular automata, or QCA for short. And I will introduce it later. It turns out that it's possible that this 1D QCA is beyond 1D unitary circuit in the sense that this QCA could be can never be implemented by the 1D unitary circuit. Moreover, you can try to introduce different boundary conditions. Say you can make this orange circle a bit thicker, and you can try to modify the unitaries near the boundary. But what's happening is that no matter what you do, this 1D QCA is always well-defined modulo 1D unitary circuit. So in other words, this 1D QCA modulo 1D unitary circuit is an environment that is fully determined by the bulk. So you can say there is some kind of bulk edge correspondence going on. Okay, and here is the one-page conclusion of our work. So we are trying to generalize this story of the unitary circuit to the measurement circuit. So in the unitary case, we have local unitary circuit, where the counterpart in the case of measurement is what we call locally reversible measurement circuit, or LRMC for short. And in the unitary case, we have QCA, and in the measurement case, we have what we call measurement quantum cellular automata, or MQCA. And it's well known that for 1D QCA, there is an index theory called GNVW index. And in our case, we have a similar index theory, and what we call it MQCA index. And we also have a version of the bulk edge correspondence, and we will use this kind of correspondence to solve the puzzle that I introduced in the first slide. Okay, so now let me introduce our work line by line. So the first one is the IORMC. So by a measurement being reversible, so yeah, like the most famous example for measurement being reversible is probably the quantum teleportation, like this. So as you can see, using biomeasurements, the quantum information that is stored in this qubit is not destroyed by the measurement. Instead, it's just teleported to a different qubit. And another version of this teleportation is something like this, where there are only 2 qubits involved. You first measure ZZ on both qubits, and then you measure X. So the common feature of this quantum teleportation protocol is that the measurement is not destructive. Instead, it's reversible in the sense that you can reverse the whole process by a different measurement. And what we call locally reversible measurement circuit is something like this. So you have a measurement only circuit, where each measurement step is reversible in the previous sense. And what's more, we demand that in this protocol, the information must flow locally. I will not introduce exactly what we mean by information flows locally, but I will just tell you one example. So the example is what we call a shift by measurement. So here, for example, you consider this 2 layer. You first apply ZZ and X. Now, it is simply something repeated. You just repeat to apply this protocol like one by one. So here you can see after 1 layer, the information on the first qubit is going to teleport it to the second qubit. And now you add another layer of Z and X. Now the information is teleported from the second qubit to the third qubit. So the net effect is that you realize some kind of shift, so that information is shifted from the left to right. And of course, the Floquet code is another example of the locally reversible measurement circuit, and that's why this notion is relevant to our talk. Okay, the first result of our work is to fully classify all kind of 1D locally reversible measurement circuit. So even without any dynamics, we proved a structure theorem for all the 1D stabilizer group. So we proved that the 1D stabilizer group is always equivalent up to on-site Clifford. It's going to independent Ising chains and independent qubits and Bell states. And note that for each Ising chain, you actually have a ground state degenerate of 2. So it behaves like an effective qubit. So morally speaking, you can view a 1D spider group as some branch of effective qubits. And we show that the 1D LRMC is nothing but the Euro unitary QCA for this effective qubits. Okay, and this is for the first object, the first line. Now, for the second line, let me introduce the QCA. The QCA sounds like some kind of big name, but it's actually pretty simple. The QCA is a unitary that preserves locality in the sense that it maps a local operator to a local operator. So one example of the QCA is a finite depth quantum circuit, where it preserves locality simply because you can draw the light cone so that you can say a local operator is always mapped to a local operator. Another example is the shift. The shift always certainly preserves locality. So in 1D, as I mentioned, there is a GNVW index theory, which tells you that first, essentially, those 2 possibilities are the only 2 possibilities. And I need to mention that it can be proved that the translation can never be realized by a finite depth quantum circuit. So it's something what we call non-trivial. And what's more, they have a GNVW index. So this is the index as valued in the rational numbers, such that the log of this GNVW index, morally speaking, the log of this number measures the number of shifts. Okay, and in our work, we generalize this QCA into what we call MQCA. So the biggest difference of QCA and MQCA is the difference in the underlying operator algebra. For QCA, the operator algebra is kind of a tensor product of the local Pauli algebra. However, for the MQCA, we don't have this kind of very clean tensor product structure anymore. Instead, what we have is we have a logical group L, And we have a stabilizer group S, which is a subgroup of the logical group. And we consider the quotient L over S. In the QCA case, the dynamics is given by unitary. And in the MQCA case, the dynamics is given by automorphism of this quotient, LRS to LRS. And we also demand it to preserve locality in some suitable technical sense. And the bulk of our work, the technical part of our work, is to generalize this GNVW index to the MQCA index. So the biggest difference, as you can see, if we fix the underlying system to be qubits, then the GNVW index must be a value into an integer. The log of the GNVW index must be an integer. However, for our MQCA case, the integer could be for MQCA case, the index could be a half integer. So this is the biggest difference. So let me give you an example of MQCA with a half index. So in this figure, each blue dot is a qubit, and each green circle is an operator. And here, the logical group is simply is in the form of xi, zi plus 1, and the S set is simply it's simply trivial, and the automorphism is given by a shift. So each each green circle is shifted to another green circle. And if you plug in this dynamics into our formula for the index, you can see that the index is 1/2. So intuitively, it's and that's why we call it the half shift. So intuitively, it's a 1/2 shift because the full shift for the full shift, there are actually two operators above each qubit, x and z. But here you don't have one operator, so it's certainly it should be a half shift. And recall that previously we have proved that a 1D LRMC is equivalent to a unitary QCA, so it always have an integer index. Therefore, this half index must be something anomalous in the sense that it can never be realized by a standalone 1D LRMC. Okay, so for a short summary, we have seen that for 1D, there exists a quantum cellular automaton which is beyond finite depth quantum circuit, and we also see that 1D QCA is equivalent to 1D locally reversal memory circuit. And from the previous example, we also see some Merriman quantum cellular automaton that is beyond 1D LRMC. And in the following, I will apply this kind of machinery to explain the anomalous behavior of the edge of the Floquet code. Okay. So the Floquet code, as I mentioned, is a 2D example of the LRMC. And in general, we prove that on the boundary of the n+1 dimensional LRMC, there exists a n-dimensional MQCA. So here, let's consider the 1D boundary MQCA of the 2D HH Floquet code. So one possible boundary condition is like this. From this boundary condition, the MQCA can be described by this logical group, where you have two types of logicals, illustrated by those two types of green circles, and the S is still trivial, and the dynamics is still given by the shift. However, the shift is not from the from right to left. So here the index is a negative 1/2. And I wonder what does it mean? Well, it's similar to the story of the unitary QCA. So you may want to change the boundary condition of the Floquet code. However, there is still a bulk edge correspondence in the following instance. So we proved that the index of the boundary MQCA is always fixed modulo z. In other words, no matter how you change the boundary condition, the MQCA index must be a half integer. So as a corollary, there is the obstruction for you to fully gap out the boundary of the HH Floquet code. Simply because if you can do that, then there is no logical at all. There's no flow, so the index must be 0. So it's a contradiction. And in physics, what we already call this kind of thing a Z2 anomaly. So in physics terminology, what we show that there is a Z2 anomaly for the H8 Floquet code. And this Z2 anomaly is fully determined by the bulk behavior. So to be more precise, this will normally show that as long as you want to preserve locality of the dynamics, then you only have 2 choices. The first one is that you could double the period so that a half integer got doubled to an integer. Now it could be 0 modulo z. So there's no contradiction anymore. The second choice is that you could introduce some gapless boundary like this. And this gapless boundary must admit a flow which index of which has a 1/2 integer index. So okay, that's it. Thanks so much.
Thanks for the talk. We have time for some questions. Yeah, come up to the microphone.
Hey, thanks. So to me, QCAs, ordinary QCAs are a natural object in some sense, and they sort of show up in nature, like at the boundaries of systems, like you said. Do you think that these measurement QCAs sort of show up in nature in some loose sense beyond in the application to Floquet codes?
Yeah. So yeah, I think so. So the motivation of to consider MQC is to consider the case where the underlying operator algebra does not have the tensor product structure, and it happens a lot in physics. For example, in gauge theory, the physics operator should be some gauge invariant operator. So for gauge theory, there's no tensor product structure. So this is one example. Yeah.
Yeah, I actually was confused about this slide because it seems like you were making statements that were specialized to Pauli or Clifford groups.
Oh, that's true.
I didn't understand.
For technical reason, yeah, we stick to Clifford. And it's certainly interesting to generate everything to non-Clifford.
Okay.
Yeah.
Because you could imagine some like fermionic
yeah, also fermionic
version or something
right,
very fancy that
but in QC in literature it's quite often you first to consider a Clifford version. Yeah.
Okay. Other questions? Okay, let's thank Zili again.
Thank you.
Thank you.